All right, where was I? Okay. Let's not worry about that or that. Get out of here. All right. You're not gonna see my cursor anymore because OBS was lagging like crazy. Got some blueberries because I love blueberries. All right, let's go map my ears on headphones. I guess, bro. I guess. So how we're gonna do that? Let me just make sure this is committed. Yeah, we're gonna need that. Git add source. Git commit. What do we have? 1 over n, 1 over n squared, 1 over n cubed waves. All right. Sorry, I just saw something really funny. Okay. Let's go ahead and wipe out these real quick. And what we're gonna do is what do we want to do? We want to bring this thing back. Should we save this somewhere? Yeah, you know what? Let's save this somewhere. Just like, I don't know. Maybe. What do we do here? We have L. We have L star and we have note. Why is it so slow today? Jesus. Square wave. I'm just gonna hush. This is not gonna compile, but it's okay. Get the square wave out of here. Okay. You know, let's get some royalty-free music going, just for a second. All right, void sawtooth. What is this? 1 over n cubed? I mean, whatever. I don't care. Instead of multiplying by semitone I'm gonna do something like this. Pow note to the 1.5. So this will go through a bunch, I guess. Oh wait, hold on a second. There's a better way to do this. Not to find it exactly what my hearing is, but I believe, yeah, we can just do that. Okay, why is my MacBook just killing? Just maybe. Ooh, that's even worse. Oh wait, it's logarithmic, right? So what if we did 2 to the x? Oh, that goes even faster. Okay, no, I like maybe x squared. X squared. Right? Yeah, x squared. Okay, 2 pi x squared. That's fine. We can just do that. So, what is x exactly? X is time. So, what we're going to do, pretty simple. And the nice thing about this is that it's perfectly continuous. So, let's do this. We'll do sample count. Oh, wait. Wait a minute. No. X squared is slower, so let's use x squared then. I'm not even gonna do any like magic here. I'm just gonna do this. No rest either. So we're gonna do x squared. There we go. Easy, right? Sample frequency. Do we need that? Let's start at like. Oh, we don't even need node actually. Yeah, we don't need node here. Let's see what happens. We might want to divide this by a lot. Or we already are. Let's see what happens. Whoa! What do you mean it's undefined? Oh, is it num samples? What? 157? What did Chopin, what did he write? Oh, Nocturne, okay. Okay, let's try this. No, we still have a bunch more errors. Oh, right, L star is not defined. Should we just do, what is L exactly? What is effective amplitude? What the fuck, dude? Gotta let me know these things. I love this song. SF32, okay. Yeah, Beethoven was onto something when he wrote this. Wait, let me just make sure the audio's good. Alright, audio's good. I think... I believe this is a F64 star. You know, I'm curious, how would you even dance to this kind of music? Alright, go. Ah, shoot. Okay. Rest duration milliseconds. You know what, man? Go. Fuck. What is note? F32? This is like specific to each shape. Oh my god, fuck off. What is no duration? Is it a U32? U16, okay. Close enough. Talk to me. Okay, here we go. Beethoven, I'm gonna have to pause you for a second. This is more like 2E actually. Let me 2C. 2E. Nope, 2E. Nope, 2E. Go. Alright. Get that Safari out of here. Where was I? 2E. Impeccable. We have created something. I don't know what though. What the fuck? Alright, let's see if we can actually model this. What the fuck is going on? So, also, I think we can close this. We've already figured out the whole format. So it doesn't like this, does it? Okay, why not? Sine of 2 pi jj. Okay. What the hell? What's going on here? What if we really slow it down, like by 48,000? Okay, but you still have to consider that. Let me make it. Let's make the y-axis much smaller. So just negative like 2 to like 2. Okay, so oh my god, maybe we really need to slow it down like times 48. Okay, this could work. We needed to go from like basically, you know, 0 frequency to frequency 44. Wait, there. Yeah, let's just slow it down, see what happens. Sample frequency. So this is like 48,000. Maybe this should slow it down. Let's find out. All right. I think it's getting aliased. I think that's what's happening, but I have no idea. Let's hear it. Oh! Okay. Well, this actually tells us something. When do we start hearing it? I need my headphones for this one. Oh! 49. About 49 seconds in. Now, let me tell you what the exact... hold on a second. Oh, wait, I hear that. Wait. Actually, it starts earlier. Now, let me figure out what the exact frequency at that point is going to be. So about... 17 seconds in, I hear something. 17 seconds in, I hear something. Let me just make a note of that. What is the effective frequency at that point? 17 seconds in. That's going to be like sine of 2 pi 17 times 48,000 times 17 times 48,000 divided by 48,000. 48,000. All right, so we have some, well, it doesn't really help us, but what is 17 times 48,000? Let me just mark it. Right about... Oh, sorry, here. Right there. That's when I first start hearing it. And this looks like a frequency of roughly... Okay, so what is this value? Looking at is this frequency or is this what am I even looking at here? Oh, this is sample. This is how many samples. Okay, so if you do the math here, I can hear it. Let's say I can hear it at 1700. Let me just confirm that one more time. Yeah, like 16. It's more like a feeling than a... Yeah, let's say 16 seconds. Like a earthquake. It's not like a sound, it's like an earthquake, like a beat in your heart, you know? So anyway, 16,000. So right around that point, the number of samples that makes up a phase is this number right here. So x is equal to, what, 769,500? Is that it? Or is it exactly, maybe 498.55? Close enough. Okay, so now what we're looking for is, how many samples is that? It's looking at that many samples. No, this many samples. 1498. 1498. So that's how many samples. That's That's how many samples it takes to go through an entire wave. So in 1 second, there's going to be 48,000 samples. So this thing is going to repeat that many times in a 1 second stretch. And 1 second, how many times something repeats in a second, is known as hertz. GG, roughly 32 hertz. I know my ears are awful. Right? Where is it? All right. Wait. Okay, let's keep going. Keep listening to this thing. So the frequency is like x squared. Wait, why can't I hear it? Oh, there it is. Because these speakers suck. It's very quiet. It's like a well, don't stop now. I was. $200. Damn, I was getting excited too. Damn it. I want to know what happens next. Come on. All right. Maybe you can hear that. It's so slow. It's happening. It's happening. Come on. It definitely feels louder. So I know that like different frequencies are experienced at different like loudness for us. Okay, I'm gonna 10x that actually, it's too slow. Here, sample frequency. Let's just throw in a times 10. So let me just throw in a times 10 into that graph real quick. Right here. Yeah, why not? Just completely mess up all my calculations, but it's okay. Make main. Alright, so just go 10 times faster. Just too slow for me. Let's hear it. Come on. Oh. Much faster. It's loud as fuck. How many hertz are we at? It's taking too long. I feel like if it gets too high, it's just gonna start aliasing. Seriously? Still too slow? Alright, 100. Let's throw another 100 in there. Where are you? There. Open with QuickTime Player. And we have liftoff. Oh, she got quiet. Okay, let me get the headphones on. I think we've found a little something. Found our niche, I guess. I'm diving in. Let's see how fucked up my hearing is. Hang in there. That's it. Oh. Yeah, it's definitely aliasing at this point. I can hear this. I can hear that. But like, yes. Yes. Maybe like here. So maybe 124. Yeah, maybe like 124. So we're looking at about 84 seconds in, so, or 84 times, x is equal to 84 times 48,000 sample. Where are we looking at? This is going to be way out there somewhere. Oh my god. Where is it? 4 million? Somewhere beyond the sea, somewhere waiting for me. Here we go. Yeah, it's gonna work. We're deep in it. We are so deep in it. Okay, well, you can pretend this is a sine wave, or we can just do this. Hold on, it's not that hard. Y-axis, -2, 2, done, easy. All right, so right at this point we have a. Looks like the phase is about. What is this? The phase is 304 whatever, all the, where'd you go? All the way to here. So this is how many samples apart we're hearing, which is only 2 samples. 2.85 samples. That's how many samples apart we have. And we're going to do the same exact math. We're just going to say 48,000 divided by that, 2.85. And that is how many hertz we are hearing. Oh god. Yeah, my hearing is really bad. I can't even hear 20 hertz, 20k hertz. Too much damn coffee or something. All right. All right. Well, that's fun. My hearing is roughly 32 hertz to 16.8 kilohertz. Wow. All right. Whatever. Let me do actually hearing test hertz. Oh, it's gonna hurt all right. All right. Global. Shut the fuck up. Here we go. Get ready. Yada yada. Here. Whatever. Let's hear it. Gender male. What are we doing? Just. Jesus Christ. Oh my god. Alright, no traffic. I gotta close the door before I record because Oslo don't know how to be quiet. In here. No, Alright, it's gonna fucking like start screaming at me. Watch this. Alright. Okay, no, this hertz, hearing, range, check. Oh my god. All right, let's do this. Okay, let's see what's going on here. No. Wait, that was quick. Okay, I can hear it. Just kidding. Yeah, yeah, it seemed to be like around 30, 32 to, yeah, this is correct. Okay, yeah, 16.8K. Let me, all right, whatever. Cool. So that's, I think we can call this one done. Map your ears, yada, yada, yada. All right. Ooh, deliverable. Additive chord. 4-note A minor chord, ACE, octave A. Each note built from a fundamental plus 8 decaying harmonics. Okay, that's that's pretty easy. Let me get that up for you real quick. So, git let me do move to E golden git add dot git commit quick hearing check. Okay, let's get rid of this. Let's get that A note. So we're gonna do something probably similar to this, except we're gonna do it with a triangle, because I like triangles. Let's see. So we're just gonna do a single note for 5 seconds, or I don't know. Yeah, 5 seconds is fine. All right. Let's see. Oops. Okay. We'll start with yeah, A4 is fine. 4 U32J is equal to 0. J is less than, okay, this exact thing. So we're gonna go through all these and we're actually gonna add to the same exact one. Something like that. So we'll just do, we're gonna need to pass left somehow. So probably triangle something something left. What that is gonna be is F32 base is equal to note. F32 third, minor third is equal to base times semitone molt times semitone molt times semitone molt. Right, this is this right? Minor is 1, 2, 3, yeah. We're gonna do fifth is gonna be minor third times 1, 2, 3, 4. 4 of them. If you're curious, I'm visualizing a violin. I know this is dumb, but I don't care. Okay, or, I mean, it's like, oh, wait. We could do like this, like that, maybe. Something like that. That's, Kinda. It's close. It's close. It's not exactly equal temperament, but whatever. Octave. You guessed it. Yeah, okay. So what we're going to do is we're going to do triangle. What's the actual triangle API? I just wrote it. L, so L is actually left is just going to be the first parameter there. We're going to take note, which is going to be, first one's going to be base, then we're going to do effective amplitude, whatever, amplitude, and we're going to do note duration is going to be the same for all of them. Oh. Oh, we already had the for loop. We don't even need the for loop then. Okay. Bye-bye. See if it works. And the last one is, no, that's it. Okay. I guess we could pass in level, but let's just see what this sounds like first. Sounds like with one of them. And I think I will actually pass in level. Was it U16 levels? And where are you used? I'll do, what, you said 8? 8 sounds good. Let's hear it. We probably don't need all that much, though. We don't need 200 seconds. We just need like 10, maybe. And then it's just going to be silent. M2, this guy. Go. Let's hear it. Beautiful. Let's bring in the fifth. No, we don't need you. Right? Try that again. A little trouble there. Try the fifth. Funny guy. Talk to me. Nope. Not quite my tempo. I don't hear it. Oh, because we incremented left, didn't we? So it's gonna sound like, let me guess. And then it's gonna go higher. No? Wait, what? Huh? All four of them at once? Oh, right. Oops. Let's hear it. Although it's still not gonna work. Or it did. Wait, but why did... We do L++. Why does that not affect... Oh, because we copy the address when we pass it in. If we were to actually modify the address that it pointed to, we'd need something like this. But we don't do that, so this works fine. Close out a few things real quick. You know what I could do? Something like, make it a bit more interesting. Little pregio. Left, you could do like left plus equal to sample frequency. And just do that each time. Oops. That's the, yeah. Okay, try that. Listen. Oh, that's a seg fault. That's gonna be a seg fault. Throwing a few extra seconds onto you. Ooh, that's another seg fault. Yeah, I hate to see it. Still a seg fault. What the fuck? Fine, 15. What? What's going on? You don't like that? I'm so confused. I'm so confused. What if I just do like one? What is left exactly? It's an F64, so go. Alright, so it's in this part. Why? Why does this make you so mad? I don't understand. Oh. Oops. Yeah, maybe don't do that. Got it. Understood. Understood. Go. Let's hear it. Amazing. Amazing. I could not have said it better myself. I think it's a masterpiece. It's a masterpiece. What can I say? That, my friends, is an arpeggio, I think. It's a thing of beauty. Okay. Two identical signs, one gradually phase shifted. If it's gradually phase shifted, isn't it just a different frequency? Anyways, I think this one's, I've been looking forward to this one a bit more. Okay, so a tool that reports peak and RMS for a whole file and per block, plus a clipped sample counter. Text output is fine. Okay. What is peak and RMS? No, don't. No, here we go. Shut up. Okay, that makes perfect sense. Okay, we're gonna do a little command line argument. Make main, but we do have this blue Rhapsody. But if we pass in meter, it won't do anything. So, and I say let's actually go ahead and fix this. So we'll do oh, we actually need an input file. Okay, this is going to become very interesting. Okay, let's completely rearrange this thing and do this. If argc is equal to 1, 2, 3. Let's check number 2. We might have to return if circump arg v 2 meter. Then we're going to go ahead and meter arg v3. Return. And what is meter exactly? I'm so glad you asked. You, my friend, are going to take a char star file, file name, and report peak and RMS for whole file and per block plus clip sample file. Right there. Alright. So we need string meter. Okay, what are we gonna do here? You know, I'm gonna put this in a new file because this is gonna be like more of a reader than a writer. Vi source meter.c, and we'll do vi include meter.c h, and we'll do vi makefile, and we'll do, I guess we're not really using rand, we'll do meter. Alright, make main. Right. If not defined, meter h, define it, end if. And what we're gonna do include types.h, or no, not even. We'll just do a void meter, and we'll do a char star file name, and that's really it. Just print out for now. Alright. Okay, that's good, and we just need to implement that. So we're going to do void char star file name, meter, and we'll actually implement it here. And we'll do include .h, and this should compile fine because we don't. Yeah, or no. Unused parameter expected. Why would you expect that? Oh yeah. Go. Oh, whoa. Chill. Non-void function makes it return a value. Return 0, I don't know. Go. Duplicate simple meter in yada yada yada. Of course. Makes sense. Go. No, still doesn't like it. Go. Good. Now we can do Blue Rhapsody meter. For loudness, let's go ahead and do let's go do this one. And it's not going to do anything, but that's fine. Now let's see how to actually build this thing, because this is going to be important. How to read this thing. So first of all, we need to get the samples, and the samples are going to be different depending on how what format it's in. So basically, we need to do the opposite of this right here, write samples. Write samples is the exact opposite of what we need to do. And we also need to read the headers first. So let's go ahead and do that. And actually, if we want to read the headers, we probably need to get all this. This probably needs to be in its own file, so we'll go ahead and do that. We'll call it include wave.h, and we'll just move all that over here. And I'll do this. And just do this, set number, and here you go. Boom, now everyone has it. We also do need to do an if not defined wave h. We'll define it. This. Now we can use it from here. Okay. Now we do need to read the file, so I think it's at the end here. Yeah. So what we're gonna do is this. Probably read binary. Open. Read binary. Yeah. Freed. What the fuck is this? Sounds good. Thank you, reference documents. Or else let's start from the top. Okay. Obtain file sizes. L size, what is L size? Long, I don't like long. Do you mean U32? Need a tel. We also need these two, IO and lib. Files go to null. We'll just exit one sounds good. Okay, file size, use 32 size, rewind. P file, allocate memory. Buffer is going to be a U8. Buffer, U8, malloc, size of U8 times size. Okay. If buffer is equal to null, then we also exit too. Different error though. Okay, then we just freed the whole damn thing. Yes. Size and file into the buffer. Result is equal to, what is result? Result is a size t. A what? Fuck off. I don't. Oh, it's U32. Okay. Okay, cool. It's now in the memory buffer. Now we can do some funny stuff like this. First and foremost, we will now do riff. Riff chunk. I mean, we don't really need the riff chunk. We can just do something like buffer plus size of riff chunk. We do need this riff chunk. This is going to be a something star, and that's going to be a format chunk. Format chunk star FC is equal to that. And I think what we need from this specifically is, we don't care about this, we don't care about that, audio format. We're just going to assume that's what we need. Number of channels is important, actually. U16 channel count is equal to FC channel count. Or numbered channels, I guess. What else? Yeah, frequency is important. So the U32. Okay. Byte per second. No, not important. Byte per block. I don't think that's important. Bits per sample is important though. Sample bits equal to FC. Alright, we just need these two, and then we can also do something similar for data chunk. Data chunk DC, we'll do that. We're gonna go ahead and skip the other one too. Data chunk, or format chunk. Format chunk, and now we can do. We need the size, so data size. DC data size, and we need DC. I think this is how it works. It's just the next one over, right? Sampled data, and we'll do U8 sample is equal to U8 star. U32 data size in bytes, data bytes maybe, go with that, right? Probably. Okay, so now we need to read this properly. Wait. What? Is this decibels? How am I supposed to know what this is exactly? Because it's just an abstract, like, okay, let me pull up that document again. Uh, not here. It doesn't say, it like I can give it in I don't know, 100 millisecond blocks, peak and RMS. I can just tell you what the normalized value is from 1 to 0. I don't know what, like, I don't know how much this is in decibels, because if I freaking change the MacBook speakers, that changes the decibels, so I don't know what the hell this is. So let's just do this. For now, just handle we'll do the 2-channel 16-bit. So we'll do if channel count is equal to 2 and sample bits equal to 16. Then we'll step through it and populate it. But we also do want F64 star. Oh, wait a minute. So we have a left channel, we have a right channel, so we probably should do the same here. Left is equal to malloc. Oh. Data size. Wait. Yeah, this is data bytes. Take the data size. Oh, got it. Okay. Data bytes divided by malloc data bytes divided by sample bits divided by 8 divided by channel count. U32 sample count is equal to that. It's like per channel. Okay, so this is useful. Okay, we'll do the same thing for right. And let's go ahead and just go ahead and step through it. How do we even want to do this? Nah, it should be a U64, or it should be a U8. So we'll do U8 star run is equal to samples. And what we're going to do is step through it very carefully. Where is it? Damn it. I had it. Where is it? I don't want to. Where is it? Oh, here we go. Almost there, almost there. Waveform. Where is it? 16-bit stereo. Low order byte left, high order byte right. Low order byte right, high order byte right. So it still goes left, left, right, right. Okay. So we're gonna step through something like this. U8 left low is equal to run plus 0. It's going to be left high, right low, right high, like that. Okay, that's pretty easy. Now we just need to do left is equal to first we need to use 16 first. Yeah, something, and then we'll do left is equal to left raw times 1.0 divided by 32768. Oh, this should be, I think this should be, yeah, it's signed, okay. And left plus plus, and same thing, same exact thing for right. Okay, let's just print out a few of these as well, just so I can see what's going on here. Printf, printf, this is 64. Left, right. And most importantly, we also need to do run plus equal to 4. And how many times are we going to do this? Many, many times. For U32, I is equal to 0, I is less than sample count I plus plus. Okay. Ooh. Now what is left raw? I think it might just be, oh, this is a U8. I don't know if we want to turn this into a U8. I don't know. Let's try this. LL. It's going to be plus LL, but we need to do LH8 maybe. I think this is gonna give us an error, but it might just work. We may need to. Fine. Let's do this. And then same exact thing for right high shifted over 8 plus right low. Let's see if this even compiles. No, not even close. 84 doesn't like that. Why not? Whoa, really doesn't like that. What is that for loop? Oh. Oops, my bad. My bad, bro. Still doesn't like it. Okay. What's wrong? What's the first one? Jesus Christ, what? Did I forget something? Oh. Go. Okay, way few errors. Meter.c p file, okay. Just call it file. Go. 2 warnings, 5 errors. That's an easy one. Go. What do you mean you don't know about format chunk? It's right here. There, format chunk. I don't see a problem with it. Still seeing p file. Where are you getting p file from? No. New. No. 2 errors. Okay, here we go. L size. Where are you? No, just regular size. Fine. I'm not dealing with anything else here. Okay, format chunk. Oh. Go. Format chunk. Oh, size. Whoops. Silly me. Go. Alright, here we go. Let's try it. So now we can do Blue Rhapsody. Or just go back a bit. There. Let's see what happens. Nothing. Amazing. Okay. Well, it's not exiting, it's just kind of ignoring me. Opening file. Just test that out real quick. No. Okay, so it fails right here. How do you pronounce a string? Printf string. S. Maybe it's getting mangled or something. No, okay, that's good. What the fuck, dude? Okay, so this is a problem with main. We're not passing the file name correctly. Oh. Can you give me a printf v2? Oh, I know why it's failing. Of course. String comp str can be equal. Okay, so we actually need an equal. Oh, oops. And 3, 2, 1. This should now do something. Nope. There we go. Very nice. Okay, well, we're definitely getting some kind of amplitude here, and then it just kind of. I mean, this looks pretty correct to me, actually. Left and right seem equal. Let me just verify that real quick by doing sneaky little right. This should be, one side should just be empty now, so go ahead and make main. This will print out this guy, and then we just run the meter on that guy. Go. VIF. Well, I'm glad I did that because wait. Funny. Very funny. So it should be swapped. But yeah, it's correct. Anyways, cool. RMF. Let's clean this up a bit. Git add include wave. That's a pretty easy one. Git commit moves shared file format stuff to new file. Git add source meter. Git add include meter. Git add make file. Git status. Git commit added reader meter file. Git add source main, and we'll do that. Okay, so that's pretty cool. We can now meter files. Make sure that works. Make main. Go ahead and do that. VIF. Now, of course, this is great, but it's 720,000 lines, which doesn't really help us that much. Let's actually do what it says, and also fix this little thing right there. All right, this is fine. Pretty happy with it. Just close out a few tabs. These are really annoying me. Let me fix these. Main 128. It's all around that area. Triangle. Wait, what? So we haven't even been doing these correctly? Oh, wait a minute. We're not even doing these correctly. Thanks for the warning, bud. And I copied it, so it's a problem here too. Okay. That's a really good warning, actually. Try that again. Fair enough. 201's not used. It's not used. Fair. Restoration not used. Fine. Any other stupid questions? I said any other stupid questions? No. 96. Frequency also not used. What? We'll use that in a second, actually. Incompatible pointer types with an expression of type format chunk. Oh. What the fuck? Actually, let me hear the new one because, oh no. Because we weren't even doing triangles correctly. And it still sounded pretty good. That sounds even better. Wow. Amazing. Actually, that's pretty important. Let me go ahead and copy to golden. Okay, status git add pretty important triangle fix. Yeah, I'd say that's pretty critical. Because right now, I don't know what the hell we were doing, to be honest. You've heard of triangles, now get ready for the octagon waveform. Alright, anyways, let's go ahead and actually do something about this. Okay, should we do normalized? Yeah, let's do normalized. Okay, cool. So we now have... Oh no, now we've completely lost the pointers to the original one. So we need F64 star L is equal to left, and same thing for right. Right. And what we're gonna do, instead of left here, we're gonna do L. And here, and right, R. There, okay. So now, what we can do is go right here. We can go we need a overall file and per block. So how are we going to do that? Let's just do per file. All right, so what do we need to do? I'm just gonna look at L for now, I guess. Okay, so we'll do L is equal to reset it back to left, and then we'll do L plus plus every time. And what we're gonna do is if, I guess peak is like amplitude, so if oh, I know. Peak. F64 peak is equal to 0.0. If peak times peak, or if F64 amplitude is equal to L. If we'll just call it amp. 64 amp 2 is equal to amp times amp, none of that power stuff. If amp 2 is greater than peak squared, we're just going to do this because actually, whatever, we'll keep this super performant. This will just easily get rid of the like they could be negative. Like if you have like 0.5, but then the next amplitude is negative 0.6, we do want that to override, so we have this multiplying thing. Okay, if amplitude is greater than that, then we have peak is equal to amp, and peak 2 is equal to amp 2. Alright, cool. That's just the peak, so we can print that out right here. Let's just do that. Why not? Printf peak was, this is a FL, long F. Peak. Let's try that. 3, 2, 1, make main. This is just pure math, basically. Where are you? CP, no. Peak was 0.049561. Does that make sense? Let me verify something. Gain. Ooh, whoa. Negative 12. I guess, but if we try negative 8, will it be higher? Let's find out. Make main. Okay, that's seriously annoying me. Let me fix that. Line 40. It's fine. Data chunk. Okay, good. And we'll do the same exact thing. Blue Rhapsody. Peak was okay, yeah. All right, so peak is definitely working. That's good. I love peak. All right, cool. It's going to be a lot louder now, though. I'll tell you that. I don't know if it's like decibels or what. This is just like my own, like, max. I mean, hey, you can make a whole beat out of this. A whole melody. Alright, where was I? Alright, so that's peak. We also need RMS. RMS is more interesting. This is called root mean squared, and root mean squared is roughly is the set of values is the square root of the mean square. Yeah, that's what I thought. Okay, so we have SQRT 1 over sample count times some, I'll just say it's like amp squared plus amp squared, something like that. Okay, so what we need to do first is get this sum. So we'll do F64 sum squared is equal to 0.0. And we'll just, this is pretty simple, we'll just do, no matter what it is, we'll do sum squared plus equal to amp2. That's it. And then once we're done, I'm going to take that method again. And we're going to take sum squared, and we're going to do F64 RMS is equal to pow 0.5. And we're going to do sum squared divided by sample count. And that's it. Let me make sure if the expected value matches what we see. Oh, no, we need to make main 110. No problem, buddy. I got you. Okay. You want math? I'll give you math. Don't do math, kids. Right. Go. Okay, RMS was 0.067445. Let's see if that matches what we expect from a triangle wave. What is A1? Can I get a sine wave? Actually, let me run the first one. It's just an A, right? What the fuck is this? Yeah, let's do that one. Oh, I know why. It's because most of the file is just empty. Like half the file is empty. That's why it's lower than this value. But okay, we have RMS, we have peak, so that's pretty cool. What I do want to do is also implement this thing, and then you really might start to be able to see the shape of this. And I think that might be the last thing I do. Null test harness. I guess so, my guy. I guess so. This one is much more interesting, and I've been circling around it in my head for a while. Anyways, let's take a look at 100. Oh, clip sample counter. Okay, and per block. All right, 100 miss a block. Why not? So basically we need to how many sample counts do we need to go through until we cross 100 milliseconds? How many samples do we go through in a second? How many samples do we go through in 1 millisecond? How many samples do we go through in 100 milliseconds? There we go. That's our answer. All right. Block sample count is equal to that. U32. Let me just swap these two. Okay. Right. Okay. we want to do the same exact thing here. So we'll do block sum squared plus equal to amp2. And we're basically just going to reset all three of these right here after we print. And we also want to do the same thing if amp2 greater than block peak 2. Okay. And finally, we do exactly this. Right there. Block p equals. Okay, and block peak was great. Block peak. And we'll do block RMS. I think that's it. Oh, not sample count. Block sample count. All right, let's see it. Let's hear it. This is 100 milliseconds. Wow, okay. Block peak was, let's, that's interesting. I don't know why it does that. But you can kind of see how it, like, it gets louder. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then it gets louder. Not exactly, but like, definitely does get louder. And it goes back to that. I mean, here it's very clear. Let me get rid of that negative. Huh? We got a comedian over here, guys. Oh, fuck off. Come on. Very funny. Okay, a little bit cleaner. A little bit off perhaps, but yeah, you can kind of see it go up and then down, which is kind of what you hear here in terms of loudness. You just have more and more things added as you go. With QuickTime. Okay, cool. Oh, we also need one more thing. That's going to be the consecutive, the clip sample counter. Clip sample counter music. Oh. When his amplifier is overdriven and goes beyond capacity. That is in odd order. Oh, okay, I see. So if we have multiple, okay, we need a clip counter as well. Let's get it. Clip sample. U32 clip sample count is equal to 0. And what we need to do is we need to do U8 is in clip equal to 0. Okay, so we're gonna do a little check here. If we need amp. Wait. Don't we need whatever. Alright, so right here, once we have amp, we can do this. If AMP is equal to greater than equal to 1.0. No, maybe we don't do it here, do we? Wait, maybe we need to do it here, I think, because if left raw, if it's like, yeah, let's move it up here. If left raw is equal to, what is max? Okay, this is specifically the 16-bit case. Make main. What? Right. What do you want? I'll give you D. Go ahead and meter it. Should be fine. Should be perfectly clear. 0. Damn right, we didn't even get close. Cool. Git status. Git add RMF. Git add source. Git commit peak RMS and clipped sample count are metered. Push. No push. Alright, cool. 3A is done. The null harness test. Well, this is going to build on the reader, but instead of measuring the samples and doing statistics on them, it's just going to compare against 2 of them at the same exact time. Which is great because if there's a left track and a right track, we have multiple comparisons to make. And meters the residue. Yeah. I really want to get to this. This is going to be so cool. And this seems pretty cool too. Anyways, take a break.